My name is Emil NJOR. I'm coming from this Technical University of Denmark, so quite far away from home at this point. And I'm going to be presenting this work that we've done on what we call data-aware neural architecture search. And I'm going to try to keep it at a very high level for you guys here, as I believe that we are from many different fields. I heard some guys that I talked to earlier today that barely knew what neural architecture search was. So hopefully you'll all be able to follow what I'm going through here. I'll start by talking about what I would call a traditional neural architecture search, as it was introduced back when people came up with neural architecture search. So basically, neural architecture search is making a computer search for a neural network architecture that's going to perform well for a given use case. And in the beginning, we used a single objective, typically accuracy, that we want to run through this neural architecture search and get out a model that optimized the accuracy. However, when we want to deploy models on tiny devices, which we all want to do here, we can't just care about the accuracy if that means that our model is going to be humongous and it'll take a lot of memory to store. We also have to care about some resource constraints, and there's really a lot to consider. I've just mentioned a few here: memory, compute, time, and energy. So then some smart people came up with what has been known as hardware-aware neural architecture search, where we now have multiple objectives. You probably still have some accuracy you want to achieve, but you also have some memory constraints you want to stay within, and some energy constraints, and so on. Then you run this through your hardware-aware neural architecture search, and you get out a bunch of models on what we call this Pareto frontier of models, where it's not possible to improve one of these metrics without also deorientating another one. So the big question that we asked when we were going to start this research was, is there any way that we can try to improve neural architecture search for tinyML even further? And to start to answer that question, I'd like to go through the stages of what I would consider a typical tinyML application, where you have some sensor that you use to sense some data, then you pre-process this data, put it into some machine learning model, handle the output of that model, and finally use it in some application. And each of these stages consume some of these constrained resources on our tiny device. So for example, when you're sensing data, you're likely having a sensor that's consuming some energy. You're going to have some memory to store this data that you're sensing. And then in the later stages, such as when you're pre-processing data, when you're running inference on your machine learning model, handling the output and the application and so on, you're all the time processing some data and saving the results. So you're again consuming some compute, memory, time, and energy. And this is really what we want to try to minimize when we are creating tinyML applications. And we came up with primarily 3 ways we could think of to reduce these consumed resources. One is the model. That's what's been optimized already in hardware-aware neural architecture search. We could try to optimize the application, but that can really be anything, so it's very hard to generally optimize. But one thing that we thought hadn't been played around much with was the data that you put into your model and that you use to both train and run inference on these models. And before I go on, I'd then like to introduce this term that we've also used in our paper, which we have termed data granularity. So imagine that you have two different microphones in the same environment listening to the same sounds. One is capturing the sounds at 48,000 hertz and using 16 bits to store each of these samples. And the other microphone on your right is capturing data at 24,000 hertz and using 8 bits to store this data. They're both listening to the same data, but one is capturing a lot of more information about said data. And there we would say that the microphone on the left would be having a higher data granularity than the one on your right. And the key insight is that maybe it's a bit obvious, but we can save resources by lowering this data granularity. So for example, when we sense data, if we have to sense less data, our sensor will consume less energy, hopefully at least. You might be able to even buy a cheaper sensor that doesn't need to support as high of a sample rate as a more advanced one. You're going to need less memory to store this data. When you're pre-processing the data, you're also going to have less data to pre-process, again saving a lot of resources. During the inference, at least if we're talking neural network models, your input layer will typically be smaller as your data is smaller. However, when we get to the handling output and using this data in an application stage, the optimizations are less clear. Maybe you could say if you're using autoencoders, then the output will also depend on the data that you're using. But for the general models, there should be small changes. So now we can try to take a little bit of a step back and consider how you have the relationship between the size of the data, so how many resources are consumed by the data, and how many resources are consumed by the model for our traditional hardware-aware neural architecture search. So here we are not in these hardware-aware neural architecture searches. We're not really considering the data granularity. So this data box is a constant. It can't be changed. So we have a set amount of resources that we have for our model, and we're going to have to do the best we can given those resources. But it could be that maybe you can reduce the amount of resources that are used by our input data and use those resources to construct a more advanced model that's maybe going to give a better predictive performance. The other way around, maybe we could also give more resources to storing more information about our data and using a smaller model, and that could also provide better results. And this, of course, all depends on the application that we're deploying a solution for. So that's really where our idea of data-aware neural architecture search comes in. So it's kind of an expanded neural architecture search. You could also say an expanded hardware-aware neural architecture search, where we along with trying to construct a neural architecture also try to optimize the data granularity of the input that we plug into this model. And it, of course, sits in this larger area of AutoML. We also created a very simple implementation of this data-aware neural architecture search, where we have so typically a neural architecture search consists of 3 stages or 3 components. There's a search space, that's the space where you find your solution. There's a search strategy, that's what you use to explore this search space, and a performance estimation strategy that's used to judge the quality of the solutions that you're finding. So in the search space, we have this data granularity search space of different ways that the data can be configured. and we have a layer search space for layers in our neural network architectures. Then we use a search strategy that's based on genetic algorithms that we initialize in a trivial way. And we estimate the performance of our models systems, really, because we're also including the data by considering the accuracy, the precision, and the recall of the systems that we design, along with the model size of these systems. And we try to use this quite simple implementation to run some tests on this toy Atmos dataset that contains recordings of toys in normal and abnormal operating conditions. And we kind of have to be able to classify a sound as being abnormal or not. And we did this in two settings. One where we allowed our data-aware neural architecture search to optimize this data granularity, and one where we said data granularity remains the same. And then we tried to run this data-aware neural architecture search. And as you can see, in both cases, we're able to get an F1 score of 1. So it's a perfect score. The data set might be a bit easier than many others. But when we're using this data granularity optimization, we're actually able to construct models that have a model size that's up to 4 magnitudes smaller than we're not considering these data granularity optimizations. Okay, that was a quick introduction at a high level to this work on data-aware neural architecture search. Just to reiterate myself, this is me. I'm a PhD student at the Technical University of Denmark. I'm about halfway through my PhD. A PhD in Denmark is just 3 years, but I still think I have time left to try to start up some new work with maybe some of you guys, if any of this sounds like something that's interesting to me. There's obviously still a lot of work to be done on this, more experiments to be made, more interesting metrics to be evaluated. So if you have any questions, any ideas, or so on, feel free to contact me on this email that you see here. Otherwise, I just have a few attributions to some of the figures that I used throughout my presentation. And then I'll just thank you for your time, and I believe I'll be taking a few questions now. Thank you.